The objective of this video is to review rotor slip and determine the induced voltage in rotors of asynchronous machines. This video is the first video in a unit on the induction motor, or as your book refers to it, the asynchronous motor. The reason it's called the asynchronous motor is because the rotor rotates at a speed different than the synchronous speed of your air gap fields. That is, your rotor rotates at a speed called omega r, while the fields in your air gap rotate at a different speed called omega s. So the rotor is asynchronous. The assumption in this unit is that you have some familiarity with the induction motor already. In this video, we're going to review the concept of rotor slip, and then we're going to derive the induced slot voltage of the induction motor's rotor as a function of slip. So let's get started with reviewing slip. So I've written an expression for the air gap field, the magnetizing field of our machine. And I'm showing that that field is produced by the stator winding. Because remember, in an induction motor, there are no permanent magnets. Your only source of MMF for the magnetizing field is the current linkage of your armature winding. And I've got an expression here for armature winding. You can recall this expression from our previous lecture on harmonics in the air gap of AC machines, as well as going back to our rotating current linkage video series. And so our stator winding is responsible for producing a rotating current linkage that produces the magnetizing field of our machine. And from this, we can determine an expression for how fast the magnetizing field rotates in our air gap. And we get this expression here in the blue box, that our stator field, or magnetizing field, is going to rotate in the air gap at a speed of omega by p, where omega is the synchronous frequency of our electric machine. It's the frequency of our stator currents. And so we're going to start to summarize here the key rotating components in our machine. And we've already reached our first item to summarize, which is that our air gap field travels at speed omega s. We can draw this in the air gap of our machine. It's a little bit more complicated than when we had permanent magnets, but we can still depict our air gap field, our magnetizing field. So I'm drawing this expression here, and I'm showing that the field is peaking at this location here, which is omega s times t. So as time marches onwards, this field rotates counterclockwise. I'm drawing this intentionally to look like permanent magnets. So in the past videos, we've drawn permanent magnets as these green and red shaded areas where they are establishing the magnetizing field or the dominant air gap field. Here, we don't have the permanent magnet, so we're instead going to just indicate by shading zones in the air gap where the magnetizing field is a north or a south pole. And I've drawn this for a two-pole equivalent rotor. So the field peaks right here. We have a radial component out here, but it's smaller magnitude. Here there's no component. Now you got a south pole. Here's the peak of the south pole, which is 180 degrees, opposing the north pole, of course. And in addition to this, we have our rotor rotating. So the rotor rotates at speed omega r, and as we mentioned earlier, the rotor speed is different than the stator speed. Omega r does not equal omega s. And so we introduce this concept of slip, which is defined as the difference between the rotor and the stator speed. Whenever we talk about slip, we don't talk about it in units of radians per second. We always talk about it as a per unit quantity, where it's defined like this. Slip is equal to, slip as a per unit quantity is equal to the stator speed –
（– – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – –– –– – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – –
And we can solve this for the rotor speed as being 1 minus s times the stator speed. And we can talk about 4 primary cases of interest for slip. The first is when we have a locked rotor, where the rotor is at stall. That means the rotor speed is 0, which corresponds to slip equal 1. The second case is more generally where the rotor speed is simply less than the stator field speed. And this is the standard motor operation regime. The third case is where our rotor speed is actually equal to our stator speed. So then the rotor is rotating at a synchronous speed. It's synchronized to the stator field. And in this case, slip is 0. And we're not able to make any torque. An induction motor can make no torque when its slip is 0. And this is sometimes called the no-load case. The fourth case is where our rotor speed is actually greater than our stator speed. In this case, slip is less than 0. It's a negative quantity. And this corresponds to our induction machine behaving as a generator. So this is generator operation. Okay, so these are the 4 cases of interest for slip. Let's talk a little bit more about this rotor. As I've drawn it up here, this is my attempt at drawing slots in the rotor. So we've got rotor steel out here, and then here where I'm highlighting in red are slots that carry conductors. And there are 2 categories here for what you might have on your rotor. The most common type when you talk about an induction motor is that you've got bars in these slots that are short-circuited on either end. And that's called a cage rotor because it looks like a squirrel cage. So as we're viewing this right now, you'd have a short-circuit connection that would be soldered to all of these bars on the end that we can see out of the page, and then on the other end of the page, you'd again have a ring that is soldered to all of these bars, and that is the conventional squirrel cage machine. Alternatively, you can have a standard rotor winding in here. So that is the second type of rotor you might have. And when you install a rotor winding in here, you can design it much the same way as you would design a stator winding. And then you either short circuit the connections, and so in that case, that winding behaves a lot like a squirrel cage rotor would behave. Or you could connect its phase connections via brushes and slip rings out to the stator and manually inject currents into the rotor. And that is called a doubly fed induction machine, or doubly fed induction generator. And that class of machine allows you to operate your rotor at speeds that are very decoupled from the stator frequency. And we're not really going to talk about that in our lecture series here. Instead, we're going to focus on the case where your rotor winding is short-circuited. So it's either a cage winding or it's a wound rotor with multiple turns, and then the phase terminals are short-circuited. And really, most of our focus is going to be on this cage rotor. In this video, we'll entertain both concepts, but going forward, we're going to focus on the cage rotor because that is the most common type of induction machine by far. So in this type of rotor, where you've got a short-circuit connection of your rotor coils, you can draw what's called the torque speed characteristic of the machine, or the torque slip characteristic. And when you do this, on the y-axis you're plotting torque, and on the x-axis you're plotting either rotor speed in units of radians per second, or you can plot it as slip, and we're going to plot it as slip. So this again could either be rotor speed in units of radians per second, or the ratio of rotor speed to stator speed, or slip. When your rotor speed is equal to your stator speed, that is omega r over omega s equals 1, slip is equal to 0. That is this case over here. And when your rotor speed divided by your stator speed equals 0, slip is equal to 1. And when you plot your torque speed characteristic, it's going to look something like I've drawn up here. Let me clean up my drawing a little bit. Where at 0 speed, you've got a torque value, and as your rotor speed accelerates and approaches a synchronous speed, your maximum torque that you can create actually increases. And then when you cross the point that your rotor speed equals your stator speed, you are able to produce zero torque. And as you continue to accelerate your rotor, you're actually creating negative torque. That is, it's entering a generator operation. And this peak value of torque up here, this is called your breakdown torque or your pull-out torque. And it's referred to as TB. The corresponding slip is referred to as SB, your breakdown or your pull-out slip. This type of characteristic is what's predominantly used to characterize induction machines that are line-fed or connected directly to the power grid. Because you can see what will happen is that in these cases where you don't have any kind of variable speed motor drive, when you turn the switch on, when you turn your breakers on and your motor drive, your induction motor is directly connected to the grid, you're going to start out over on the left side here with a slip of 1. So the rotor is at 0 speed and you start out with a slip of 1. And as long as the load that's attached to that motor requires less torque than is created at this speed, your rotor will start to accelerate. And as it accelerates, more and more torque will be applied to the rotor until you reach this peak torque value, and then you keep accelerating, and less torque is being applied to the rotor electromagnetically until you hit the point that your load is sitting at. And so usually these machines are designed for a rated load torque somewhere in this red region here. So around half of the breakdown or pull-out torque. And the reason that the torque is designed for this rated torque is that you can see if you suddenly have an increase in load torque, your shaft will slow down a little bit and it will self-regulate. So when you have too much load torque and your shaft starts to decelerate, as it decelerates, the electromagnetic torque builds up until it's able to match the load torque, and then you have a new operating point somewhere else. Whereas if you designed your rated torque to be up here and all of a sudden your load started creating more torque, you can see you'd be in an unstable condition. Your rotor would slow down, you get less electromagnetic torque, and finally you just come to a stop. So that is the case with a line-fed machine. With an induction machine that's operated by a motor drive, you have the same situation, but now you have more controls at your disposal. You're able to actually modify both the voltage magnitude of the stator voltage and the frequency of it. And so while you still have this kind of torque speed characteristic, you're able to move things around a little bit to operate the machine in a more favorable circumstance. You might be more comfortable operating closer to your pull-out torque. Okay, so that concludes the first part of this video, which is on reviewing rotor slip, and the rest of the video is going to be focused on induced voltage in rotors. Before we do that, let's summarize the key things that I want you to remember. So this definition of slip is going to come up time and time again in the induction motor unit. It is critical to remember, as well as the speed of the stator fields in the air gap of the machine. The third thing that I want to point out is that our total air gap field in an induction motor is our magnetizing field. This is the complete magnetic field in the air gap of the machine, and it is produced by the stator winding. And so we're going to be going back frequently and thinking about how we make fields in our machine based on winding factors and coil placement and all that, and whether or not the fields were created from the rotor or they're created from the stator. Okay, now let's move on and talk about induced voltage. And we're going to start by recalling some details from our Star of Slots lecture video. So if you remember back a few weeks, we drew a synchronous rotor surrounded by stationary coil sides, and we calculated the voltage in each of the coil sides, the voltage that's induced in each of those coil sides. So I'm going to sketch that here, and we'll quickly summarize that, and then we're going to use those results to explain the voltage induced in the slots of the rotor of our asynchronous machine. Okay, so we had this situation here where we've got our rotor that's rotating in the counterclockwise direction, And then we've got surrounding the rotor, of course, our stator and the stator coil sides in slots. And so this, I'm just recreating diagrams that we had drawn in that video. And so we're summarizing the facts here. We have stationary coils, the field is rotating counterclockwise, and we're going to use the Lorentz force equation to calculate the EMF in the machine. And so you can see that the Lorentz force equation says that you're going to get a force produced on a charge that is in the direction of the velocity of a charge, the cross product of the velocity of the charge and the magnetic field. Now, in this case that I've drawn here, the charges are stationary because the coils are stationary. But in that video, we know that this is really the same thing as if the coils are rotating in the clockwise direction while the field is stationary. And so when we set up our integral to calculate our EMF in the coil side, we came up with this expression here, where we place this negative sign in front of v to recognize that that v is actually the velocity of our field. It's because of this fact here that the coils are stationary while the field is rotating, whereas the Lorentz force law is set up for the coils to be the ones that are rotating. Okay, and I'm pointing this out because that's going to be an important detail as we try to apply this to our asynchronous rotor. But before we do that, let's summarize a little further here. And so this was the punchline here. We determined that our slot voltage was equal to our velocity of our field times the field at the location of a slot. So that's why there's an alpha slot here, times the length of a coil. And we got that by evaluating this integral. So alpha of a slot is just as you're rotating this way, right? It's this angle as you go that way. So now we'll sketch the situation for an induction motor. So for an induction motor, our field is rotating and our rotor is rotating. And the relationship, again, between omega r and omega s is defined by our slip. So, well, for the stator winding, where the coils are fixed, we can just say that the relative motion of the stator coils is the opposite of the motion of the field coils, or the field. But in the asynchronous rotor, rather, our relative motion of the field is to the motion of the rotor. So the velocity of the field that the rotor sees is the field velocity minus the rotor velocity. Here we can plug in that our rotor speed is equal to 1 minus s times our stator field speed, or our magnetizing field speed, and then we can simplify down to this expression here, which in fact, if you can take the next step, you can say that this is equal to r times s times omega by p. And that's satisfying to see because up here we had our speed being r times omega by p, so you can see that our relative speed to the rotor slots is the same thing but with an s multiplied in there. And then we can calculate the voltage in the slot in the same manner. And so we get this expression here, which we can compare to this expression up here. And we notice with this definition here that it's the same thing, but multiplied by our slip. So now, before we go further with this derivation, I'm going to draw yet another sketch of our rotor and use it to label some more angles. Again, I'm drawing a cross-section of the rotor. now I want to start introducing the notion of standardizing on how we draw these diagrams and the way that the angles are referenced, so that the derivation for our voltages and later on for our current linkage and equivalent linear current density, so that all of this is with reference to the same reference frame. And so what you're doing is, what I'm doing is, you can see that I've labeled the horizontal axis, and I've labeled several angles rotating counterclockwise from the horizontal axis. So the first angle to note is just some kind of general angle in our air gap at a location alpha radians from horizontal. So we've been talking about that all along with all of our machines, is that we just talk about an air gap location counterclockwise from the horizon alpha radians. But now what's new about this is I'm introducing a relative reference frame for our rotor. And the relative reference frame, we're saying that our rotor has slot 1 that's located theta mechanical radians from horizontal. So in our past diagrams for permanent magnet rotors or synchronous field rotors, we'd labeled the direct axis of our rotor as being theta mechanical radians from horizontal. So that was where the north side of the magnet was. But here we just have a cage rotor, or it wouldn't have to be a cage rotor, it could be a wound rotor, that does not differentiate a direct from a quadrature axis. We can't talk about things that way. All we can say is that we've got rotor slots. And so what we're going to do is arbitrarily just decide that theta mechanical is referenced from horizontal by theta mech radians. I mean, that theta mechanical points to slot 1. And then we're going to introduce a reference frame in the rotor, or angles referenced in the rotor reference frame. So the first angle that I've got labeled on here is alpha with a superscript r. So this is pointing to that same location, the air gap, but now we're saying that it's at location alpha superscript r, because that angle is with reference to slot 1. So same location, the air gap, but now denoted as alpha r because it's relative to slot 1. So alpha r plus theta mechanical is equal to alpha, right? Similarly, we're going to talk about our slot locations as each slot being offset from our slot number 1. So we can talk about slot number 2 being located at alpha 2 superscript r radians, or slot number 3 being located at alpha subscript 3 superscript r radians. And finally, the last thing I want to point out here is that all along we've been talking about this angle alpha c, which in our stator winding is the spacing between stator slots, and we can do the same thing on our rotor. We can call this alpha c, because we assume that our rotor slots are all equally spaced. And just like on the stator, this would be equal to 2 pi divided by the number of rotor slots. We're now ready to finish our voltage calculations. We can talk about the voltage in an individual slot at an arbitrary location, just like we did in the Star of Slots video. Where ZQ is equal to 1 for a cage rotor. If we're talking about a wound rotor, of course, then we have a number of series coil sides. And when I'm denoting voltage here, I is the slot number. We're evaluating this at the location of the slot, which is equal to alpha I in the rotor reference frame plus the angle of the rotor reference frame. So this should be an omega r. So if we're talking about slot 2, we're talking about an angle in the stator reference frame that's equal to alpha 2 superscript r plus this angle here. And now we're going to generalize our derivation to any harmonic, just like we did in our Star of Slots video. So we can write an expression for our field in terms of harmonic content like this. And we can denote the speed of our harmonic v as omega sv. And just like we had slip defined relative to our fundamental, we can also talk about a harmonic slip, which is still relative to the speed of the rotor. And if we work the math on this, just like we did in our Star of Slots video, we can get it into its phasor form. And so once we've got our expression in the phasor form, we can then move forward and write out an expression for our voltage. So you can see that what we did here is recognizing that this is evaluating the field at this angle, at alpha equals this angle. We're plugging this angle up here in for alpha here, and so we get this expression. This just travels on down over to this term, and so we'll now take the next step. We can identify this first component as simply being the voltage that would be induced in a coil side located at alpha r equals 0. So in fact, that's the coil side right here. We can combine that then with this term up here to recognize that this is the slot phasor for any other coil side up here based on the location alpha I superscript r. And all that does is it just rotates our phasor for our coil side here by the angle that the slot occurs at on the rotor. Next, we can recognize that this quantity right here is simply equal to our slip times our stator field. So we can now bring this together and drive towards a final expression. And we end up getting this cosine expression here, where our voltage in slot number I has some magnitude, which we've written out over here, times the cosine of this expression here, which has got a frequency component and a phase angle. And the phase angle is the negative of the location of our field in the air gap minus the electric angle of the slot. So let's pause for a minute at this point and think about what this is saying. If we go back to our rotor diagram up here, it's telling us that when the peak of the magnetic field is passing this rotor slot and traveling this way, that is when our voltage is going to peak in this slot. And then a little while later, when the peak of the voltage when the peak of the field passes this slot, that's when the voltage is going to peak in that slot. And that is why we see this negative Vp alpha I there. That is the electrical angle of each of those slot locations. And we can comment on the frequency that we're seeing for our rotor voltages. So the frequency of our rotor voltages is this term right here, which we can write out down here. And recalling that omega SV is simply this expression over here, and at a harmonic we end up with a V in the denominator. So if you recall this, we derived this expression in our harmonics unit, in the winding design unit, that our field speed of a harmonic is omega divided by that harmonic index times number of pole pairs. And if you recall, sometimes these harmonics will actually rotate in the negative direction. They'll rotate clockwise as opposed to counterclockwise. So for example, the second harmonic rotates backwards in a three-phase system. So just something to be aware of. If we plug this quantity here in over here, we end up getting this expression. And so this is kind of nice and satisfying to see that our rotor frequency actually ends up being our slip times our synchronous frequency. And we're now in a position that we can study the rotor winding via the star of slots, just like we did the stator winding. And so again, I'm drawing our rotor here, and we can add labels like we did before. We've got alpha C separating each of these slots. And this we can draw as our star of slots. Where each of our star of slots phasors is separated by the electric spacing of our rotor slots. and our entire star of slots again rotates in the counterclockwise direction at the rotor frequency. I highly encourage you to go back and compare this derivation and these results to what we derived and our results in the star of slots video for the stator winding. And you'll see that everything is exactly analogous, except that now we are working at the rotor frequency, which is our slip times our synchronous frequency, our stator frequency. Okay, so a couple of closing comments. The first is that if we're considering a wound rotor, we can end our analysis here. We're going to use the same winding analysis techniques as we use in a stator. It could be an integral slot rotor, it could be a fractional slot rotor. It's the same basic premise of analyzing slots for pole per phase, calculating winding factors, all of that. The whole toolbox applies. But more interesting and more challenging is when we have the case of a cage rotor. And the analysis for this is going to be considered over the next set of videos. So in the squirrel cage rotor, it's as if we have a short circuit neutral at each end of the rotor. Okay, so that concludes this video. In summary, we have reviewed the definition of rotor slip, and we've determined how induced voltages are calculated in asynchronous rotors. So we introduced the definition of slip as being this quantity here. And we talked about the speed of the stator field versus the rotor field and how it relates to slip. We discussed the torque speed characteristic of an asynchronous motor. And then from here, we use this as a launching point to dive into calculating the induced voltages that are in each slot of an asynchronous rotor. And we did that by following the same framework and analysis techniques as we developed for stator windings, the only difference being that now our coils are also moving. Nothing is stationary in the asynchronous rotor. And so we use that to work our way up to a final voltage expression for the voltage in the slot of our rotor. And we noted that our frequency of our rotor voltages is equal to the slip times our stator synchronous frequency. And then from there we were able to draw the star of slots just like we did for a stator winding, and made some closing remarks about the types of rotors that can be asynchronous.